All right, well, thanks everybody for coming. It looks like we're a bit thin on the ground this quarter, I assume, given the weather and the holidays and whatnot, but here we are. We're going to soldier on. Today we're going to be talking about our automated ingest capability as well as our storage tiering capabilities. So these are two things, Lego bricks that you can pull off and install, configure, and run without having to write a bunch of your own policy. So we'll be demonstrating that, and then we can talk about a little more about iRODS and answer any other questions if anybody has any. But today, Alan is going to be taking us through these two different capabilities. So, thanks.
Thanks. Okay. Hi, I'm Alan. As Jason said, today I'm talking about automated ingest and storage tiering. I don't have the most detailed explanations in the slides. Because I wasn't sure what kind of audience I'd be talking to. So I'll try to flesh things out a little bit more, depending on how you guys are feeling. Just tell me to shut up and move on if that's boring. So let's get started. So first, I wanted to talk about what iRODS is, just briefly. So iRODS is the integrated rule-oriented data system. It provides 4 core capabilities: data virtualization, data discovery, workflow automation, and secure collaboration. The data virtualization is provides a global namespace for your existing infrastructure, such that the data that you're managing is abstracted from the users. And they're no longer concerned about where it physically resides. And the namespace is known as the zone. We keep the information about the zone, the users, and the data itself inside a metadata catalog, which allows us to have the data discovery competency. So the metadata also allows you to take action on your data via the rule engine, which is built into iRODS. So that's the workflow automation piece. We'll be seeing a little bit of that with storage tiering during the demo tonight, I guess. And finally, secure collaboration allows you to federate with other iRODS namespaces through other institutions or companies, with just a few lines, or just with exchanging a few keys, and you don't have to exchange a lot of info for that. It's easy stuff. Right. So the new thing that we are kind of pushing recently are these things we call capabilities. These are packaged solutions to use cases that we have observed in the wild. They are meant to provide, like I said, a packaged solution rather than forcing you to write a bunch of code to enforce your own policies or whatever it is you want to do with iRODS. These allow you to just install, configure, and functionalities there. So 2 of those things are automated ingest and storage tiering, which we're going to go over now. So automated ingest is a client of sorts that we've built on top of the Python iRODS client. It's built with Celery and Redis. And it basically walks file systems or S3 buckets and populates the catalog in parallel. What this allows us to do, is register your data in a scalable way. So another piece of automated ingest is being able to extract and annotate metadata via user-defined callbacks. We'll see one of those in our demo, but there's an entire suite of different things you can do with automated ingest. And basically, this just provides a front door to iRODS for your data. So we get it in, and After that, it's up to you what happens. So during the demo today, we're going to be going over what we call the landing zone use case. The idea here is that your data sources over on the left are going to be writing to a file system within the iRODS namespace. iRODS will pick that up and extract and annotate any metadata that you want, and apply any other policy that you have set via the rule engine, and then it will move that data somewhere else. In this case, we're going to be using storage tiering for that, for the moving piece. Okay, storage tiering is the other capability that we're going to be talking about. This is a compiled C++ rule engine plugin. So one thing I did not mention is that iRODS is built as a plugin architecture. So there are a number of different plugin interfaces that it provides, and one of those is the rule engine itself. So you can provide additional functionality by just installing plugins to iRODS. So what storage tiering does is it migrates the data between storage resources in tier groups. All this, the tier groups are defined by metadata on the resources, and you can provide a bunch of other configurations such as violation criteria. In our demo, we're going to be using the default, which is time-based. So if data has been sitting on a certain storage resource for a certain amount of time, it will be migrated to the next tier. You can also do things like data verification. So you can have it check the catalog, checksums, data size. You can configure it to do any or none of those. And there are a few others, but I'm not going to get too deep into that today. Right, so this diagram, we actually have some one-pagers of this. You guys are seeing them over in the office, but essentially what happens is on the left, again, you have your data sources. You can imagine a little box where the automated ingest tool sits. That's what we're going to be trying to do. But over there on the left, the orange box is your fast storage, so tier 0. In this case, it's configured in the same tier group as the others, and it has a storage tier time annotated as metadata on the resource. And what that means is after the data has been at rest on that resource for that amount of time, it will then be moved to tier 1, which has its own tier time value and is part of the same group. And then once that time violation has occurred, it will move to tier 2. There's also a way to configure storage tiering such that when the data is accessed later, you can restage it to a faster tier for easier access. Again, not going to do that in the actual demo, but there's a lot of really neat things you can do with storage tiering. Okay, so the reason bringing these two together is important is because, well, first of all, you don't have to write any code anymore. So these two big pieces of functionality are just installed packages that you configure, and I'll show you that in a minute. And you can ingest your data quickly and then quickly take control of it via storage tiering to get it onto the storage mediums that you want. And all the existing solutions that we know of anyway are costly and create vendor lock-in. With iRODS, it's free and it's compatible with a lot of different storage resources, so you can have different storage technologies between tiers or even within the same tier, depending on your use case. and those can be swapped out at any time. So, yeah. Finally, I want to show this image. So all of this is working toward the story of your data. And what we're going to be doing is filling in the line right here between automated ingest and source tuning. What that allows you to do is unlock the rest of the iRODS capabilities once the data has been ingested. Okay. So we're going to do the demo now. Basically, I have 1,000 1 kilobyte files and 10 megabyte files to demonstrate different methods of transferring data within iRODS. We're going to ingest those files via registration. And we are going to be targeting a resource within the iRODS namespace.
What does registration mean?
Oh, sure. So in iRODS, there are two ways to create what we call data objects. Let me back up one more step. A data object is a virtual representation of a set of physical files. That set is known as replicas. And basically, the data object is just an entry in the metadata catalog. But what it's a series of entries, I guess, one for each replica. So in this case, when I say register, all we are doing is creating an entry in the catalog, which points to a physical file. The other way to get data into iRODS is to target a storage resource, which has a vault. The data is then physically copied into that vault, as well as a data object entry created in the catalog. So when I say register, we're just creating entries in the catalog. And what's going to happen is the data objects are going to be moved out of the original location since they're in the iRODS namespace when the storage journey happens. And I'll explain that as it's happening. So yeah, then we are going to execute the migration policy. Yeah.
What information do you register along with the file name? Do you register a file creation time?
Right, so there's a few different pieces of file system metadata that is automatically extracted and registered with the catalog. So creation time, modification time, size, you can configure it to calculate a checksum to ensure that the data is correctly transferred. I think those are the defaults. I don't know of any others, but you can configure it to extract additional metadata via rules that you write.
The Protein Data Bank was managing its data based upon a file creation time in order to tell which version.
Mm-hmm.
So they had to have that data from the original file system.
Yeah, and one of the things you can do with the ingest tool is implement what we call a policy enforcement point, which will trigger a rule based on some action within the system. In this case, maybe data object creation. After it's created, it can stat the file system to get more granular file system metadata. So we have that going for us.
And the storage sharing plugin also implements access time. So that's how we're tracking that
Right.
as a policy.
So in the past, the file creation time was the time when you actually imported the file into iRODS as opposed to the time it was created on the original.
Yeah.
So that's changed.
It is not necessarily changed, but the ingest, so I mean, the whole point of the automating the ingest is to bring the policy as close to the source of data creation as possible. And so we can pull all the stat information out as part of the handler for the automated ingest and maintain that in the catalog alongside of the previous system metadata that we had.
I suppose, I mean, correct me if I'm wrong, but if you're gathering, ingesting stuff from a landing zone where like a sensor was filling bits of data in there, you might like program a policy callback to say like when it was gathered, when, you know, attach that time to it when it was gathered, so you could at least, you know, I guess that's, you would source like the Unix creation time of the thing, and right.
Sure.
So you could have that time on as metadata on it as well, right?
Yeah, absolutely. Right. So let's see. For the storage tiering piece, kind of like the slide I was showing earlier, we're going to have 3 tiers within a single group to keep things simple. I'm not going to be using, they're all going to be storage resources. In storage tiering, you can actually have a resource hierarchy, meaning let's say you want to have 3 replicas of your data within each tier group. You would create a replication resource, what we call coordinating resources, and then 3 storage resources underneath that. And it will ensure that each of its children receives a replica of the data. So each tier doesn't necessarily need to be a single resource, but that's what the demo is going to be. And like I said earlier, we're going to be using the default violation query, meaning when the data has been sitting here for too long, we're going to move it. Right, so let's go over here. Okay, so right now I've got a clean iRODS instance running. What we are going to do is create a target collection called the ingest collection, create 3 resources, configure the 3 resources to be part of the tiering group, and then set the metadata on those resources to tell it how long the data is allowed to reside there.
Thank you.
Grab it.
Well, while Alan is typing, one of the things that we can do with storage tiering that is fairly unique is that everything within iRODS is driven by queries and metadata. So each one of those tiers within the tier group can have additional queries attached to it to define what a violating object looks like. So if, let's say, for instance, a user comes along and they've ingested a bunch of data, but they want to immediately archive it, they can flip a metadata flag. That would be part of one of the queries and immediately start moving the data out of tier 0 or whatever the lowest tier happens to be. And given that you could have as many metadata attributes as you want attached to anything within iRODS, you can add as many queries as you want to define what violating data objects looks like. And
So
so
you could define a high watermark and fill it too full, it'll automatically migrate.
that would be a possibility, sure. Yeah.
Are there policies within iRODS? So you had the different storage tiers.
Yeah.
Let's say least access files. I haven't accessed data in 6 to 8 months. That would be in an archive tier.
Yeah.
Or hot data is going to be in my tier 0 or 1.
Right.
Okay.
Yeah, that's absolutely something that you can
Okay.
do. Yeah. But you know, anything that you can put into a query within the iRODS query language, you could define a violating data object. Yeah.
Yeah, there's also one that we have kind of prepackaged for a minimum restage tier. So if you have data, or sorry, data sources writing to some disk that's really small, you need to keep it free and immediately move stuff off. You can have the storage tiering plugin configured such that nothing is restaged to that particular tier. So your tier 0 is where the things are writing to, but you never want to store things there, for instance.
Yeah.
You could configure it to never restage there.
Or let's say tier 0 is right next to the instrument, but all of your analysis really happens on the tier 1 or tier 2 or tier 3 because you can have as many as you want. We would just set the minimum restage tier to be not tier 0 since that may be far away wherever the instruments are, and it would just come back to tier 1.
Thanks.
Okay, so we created our resources and configured them in the storage sharing group.
You may not be able to see that all the way in the back. You want to hit return
Oh,
a few more
sure.
times.
Or plus.
Yeah.
Okay, is that, we good? Okay. So over here on the right, I put up what we call an event handler. This is basically a Python file that we feed to the ingest tool in order to tell it what we want it to do. In this case, so I mentioned event callbacks earlier. The idea here is that the ingest tool has a set of default behavior. This is how you override it. In this case, we are going to be targeting a different resource than the default resource. So all we had to do was implement two resources. In this case, we're targeting our resource appropriately named tier 0.
Creative.
Yes, absolutely. And I might as well show this as well. So this is the rule that we're going to be executing when we fire up storage steering. The idea here is that you provided an instance name, in this case, iRODS rule engine plugin storage steering instance. An operation, in this case, apply storage steering policy. And then the delay parameters basically say when should this execute and for how long. In this case, we're going to be repeating it forever after 1 second. So also the storage tier groups tell us which groups to be aware of when we are moving the data around. In this case, we're only going to have one group, so there's only one in our list.
For Regan, this is a little insider information, I guess, but for the storage, since the storage tiering rule engine plugin is written in C++, I wrote it to basically just use JSON as the rule language, which was fun. So this is not standard issue iRODS rule language.
Sorry, I should have mentioned that.
Right. So our rule engine plugins could be Python, JavaScript, Haskell, Go, whatever you want, in order to implement your policy. But since the rule engine plugin for storage tiering is just standard issue C++, I use this as a way to basically convey a job to the iRODS, basically the iRODS cron job known as the rule execution server to implement this policy, but it's all down in C++. So rather than having an additional interpreter, I just use JSON to be the rule language. So the plugin framework gives us a remarkable amount of flexibility as far as how we work with these things.
So HAL required 6 basic operations for defining a new plugin.
Yeah.
So you got all 6?
Yeah, several of them. Well, so this is a exec rule expression because it's a delayed, exec rule text doesn't do anything because it doesn't, and then the other one's just listen for the policy enforcement points that we're interested in and takes immediate action.
So you're up to 5 rule languages?
Easily, yeah, I think. Mm-hmm. Python is still by far the most popular. Yeah. But we're able to dehydrate a lot of these large rule bases into C++ plugins that can work at machine speed rather than going through the interpreter layer. So that's been pretty successful thus far, I think. Sorry.
No, please. Right, so that's the rule. So like I said earlier, the way the ingest tool is built, we will be running Celery. So these are just some what we call workers, which will be watching a queue, and the scan line that we're running down below is too big to see now, but we are going to be feeding that queue a path and a destination collection, which we defined just a couple of seconds ago. And it's just going to register all of those files as data objects in the catalog. So first we need to start our workers. This is, not that. Okay, so this is running in a Python virtual environment, which has the automated ingest tool already installed. We should probably send out slides with details about both automated ingest and storage sharing after this because they have all the juicy bits. This is just demonstrating the two working together. So So there's our salary workers. That's really big.
So since the ingest tool is based on Redis and Celery, we can just keep adding machines. So if you have a large parallel file system that you need to ingest, you can just keep adding as many computers as you want to point at it.
Yep. Okay, and this line, which hopefully doesn't happen too quickly. Okay.
Going too fast is, I don't think, a problem.
Right. So right here is how we start the iRODS sync. We've pointed it at what I've called the landing zone. I already generated a bunch of files and put them in there. But the idea is that you might be running this continuously on a cron job to watch the landing zone and continuously ingest those. And since it's using a Redis backend, it can use that as a cache to see. Oh, it's the landing zone. So not sure how that would work. But anyway, the idea is that we're giving it the landing zone to scan, and we're going to target the ingest collection. And also we have the event handler that I was showing earlier to target that resource. So here we go. I'm gonna go fast. Right. So that was just 1,000 files, so not too bad. So we're gonna stop our celery workers since they're all done. And we can see what's in our ingest collection here. So there's 1,000 files. They're all in tier 0. Actually, let me show you this. So the path here, you can see that it's still the original file. It wasn't moved or copied. It was just registered in place where it is. And we can also see already oh, sorry. There we go. So what the storage steering plugin has already done is applied an access time when the files came into the system. And that is the piece of metadata that we'll be acting on when we fire off the rule here in a second. And since we've already done this, I'm going to show it again right here. The times that we've configured are 30 seconds and 60 seconds. Since I've been talking so long, it's going to automatically be a violation for both tiers. So when I fire off the rule, we're going to watch the files drain basically into tier 1 and then into tier 2 almost immediately. So hopefully.
Oh my God, you guys did the watch thing.
Oh, yeah. Just for you. Right, so we're going to fire off the rule and then quickly move into a, oh, no, we can do the watch first. That'll be better. Sorry. Let's do that. Sorry, I learned a new trick with Tmux today that I'm very excited about, which is this thing that I'm doing. You just select text and paste it. It's great.
Copy and paste.
Oh yeah. It's new technology.
That's a new technology. Right.
Okay. So now, okay.
So our rule is a way of running a rule through the policy system that allows you to just sort of invoke things directly, rather than relying on the automated machinery on the back end to do that. So,
And so here we've got iRule. We have the -R flag to indicate which line we'd like to use. The -F to indicate that there's a rule file that we want to run from. And that's the one that I was showing earlier with all the JSON in it. So here we go. We run it. Over here on the right, I have an IQ stat, which shows jobs on the delay queue. So we have that here. And as you can see, we have files in tier 0, files in tier 1, and files in tier 2. The files in tier 1 are draining into tier 1, sorry, tier 0 are draining into tier 1 as they've been sitting there for, I don't know, 2 minutes now, instead, not 30 seconds. And then once those are done, it's going to check tier 1 to see if there's anything in violation, and then it will drain to tier 2. So, yeah, and that's basically the demo.
So you could have left Celery and all that stuff running and then just copied some data into the landing zone?
Sorry?
I mean, all of this could still be running and we could just dump more data into the,
Oh,
into
sure.
the landing zone was my point.
Yeah, I mean,
Another thing we didn't address here specifically in the demo is, since it's all metadata, resources have the ability to be part of more than one tier group. So you can envision, say, many instruments at the edge and then a common archive somewhere more centrally located. And so your archive could be a member of 5 different tier groups, depending on, you know, how things are organizationally structured within the environment.
right. Okay.
Well, let's take a look at the, give me another ILS on file 99. Did it make it?
They didn't make it. Yes,
All right,
it is
let's
in
move
tier
to
2.
tier 2. Yeah, good.
Okay. And so 2 things to note here,
Yeah.
well, 3 I guess. It's in tier 2.
Mm-hmm.
Tier 2 has a vault in, I just put it in 10 iRODS tier 2. So as you can see, this is now a different file that, because it moved it out of the landing zone into tier 1, which has its own vault, then into tier 2, which is the new vault. The other thing to note is that the replica number has increased. So normally you start at replica 0, but as the storage steering plugin moves things around, the replica number will go up. This is because it replicates the data object and then trims it once the data is at rest. So that makes the replica number go up.
If you get the file, that goes into tier 0. That's the way we've, and that will go into tier 0's vault, not the registration place, right? Is that correct?
Yes.
Yeah.
That's right.
Why don't you just get file 99, 999?
Do you have to configure that? I don't think it just does that.
Yeah.
Oh, I'm learning new things. So,
Just run an iGet to fetch the data object. It'll restage back to the lowest tier, whatever that is. And
so,
look.
whoa.
Hey.
Now he's in tier 0.
Mm-hmm.
Cool. And we should have our 1K file right here.
Yeah.
So,
So we should be able to watch the QStat
right.
after 30 seconds plus the delta for the rule engine to kick in. Yeah.
Where are you that you get the LS1K file?
I'm just in varlib iRODS, just the home directory for the iRODS user.
And that's not where you ingested it from. I didn't see where you were.
Right. I ingested from /landing zone, which is where I have the files right now.
Yeah, so we're looking to package this and take it to UNC and install it on the machines that are attached to like the light sheet microscope and whatnot to start automatically moving data from the microscopes to, you know, the iRODS server that they have there. Since it's all written in Python, we can put it just about anywhere.
And so the data's been
Oh, there it went.
tier 1 and then it went to tier 2.
You mean something about
Right on. So if you, let's say if you add the minimum restage tier to tier 1 and then do it again, it should tier back to tier 1.
Sure.
Yeah.
I'm not, I mean, I could do it right now if you want, but I'm not.
Okay.
Yell type?
What's that?
I'm gonna yell type? Or
Oh, I would go to the
we
front
just go-
page for the storage tiering plugin and then just copy and paste your way to success.
Sure.
That's why we write everything down on the internet.
Okay.
So do you see active scale fitting in here somewhere or some of your other?
Everywhere.
That's the only possible answer to that question. To be more specific, are there places where it would, being able to provide this kind of ingest at the edge and whatnot makes sense, not necessarily just
Well,
the
definitely
tier.
at that tier 3 that you had up there
Yeah.
is definitely where we would play.
Okay.
We would get your most bang for the buck.
Right.
Right.
Yeah, absolutely.
Okay, so what we're going to demonstrate now is a minimum restage tier. So here we're just adding a new piece of metadata to the tier 1 resource. It's using the keyword minimum restage tier and a value of true. So we set that, and we'll do another iGet here.
Dash F.
And the dash F is just the file already exists in the local directory, so we're going to make it not complain when we get it. So as you can see, it did not go back to tier 0 and went to tier 1 instead.
Right.
And then in 60 seconds or so, it will go back to tier 2.
Yep. Okay.
So that's the demo, I guess.
Yeah.
We've got one more slide here that I'd like to go over. So we've got some future plans for both of these capabilities. For storage tiering, we'd like to start annotating data objects with their tiering group, and then restage the data objects based on that. Right now, there's I don't know how to talk about this issue.
That's fine.
Sure. So if you have multiple tiering groups going to the same archive or the same terminal resource, and then they are restaged, there's no way to know which tiering group they came from. So it doesn't really know where to put them when it restages. So the idea there is that this would give us a way to do that. And as you probably noticed while it was migrating data, it's a little slow. So we would like to externalize the migration mechanism, probably using Celery, just like the ingest tool, so that it's in parallel. Right now, it's just using our delayed execution server, which is fine, but it could be better.
It wasn't designed for that.
Right.
It was designed for things like preservation, where you're just running checksums and whatnot periodically. The other thing with that, sorry, I keep stepping all over the presentation. The other thing is we have users who are paying for Aspira and other things like that. And so rather than leveraging iRODS to do all of the work, we're more of an orchestration engine. And so we would just, as part of that Celery mechanism, use Aspira to migrate the data or something along those lines, especially if you're going over long distances for your archive and whatnot. So we could better, extend our tentacles out into the rest of the infrastructure in that fashion.
Right. So the idea would be that you could just replace it with whatever.
Yeah.
Cool.
Yeah, exactly.
Well, we're thinking about Celery for out of the box then.
Yeah, sure.
Okay. And I provide a link for the GitHub repo if you want to see more about what's going on. For automated ingest, the main issues we're having right now is error resilience. If something goes wrong, it goes real wrong. So we want to tighten that up a bit, as well as get some better defaults for our Redis configuration and build expertise there. Finally, we would like to get containers around the ingest tool. This is sort of working at this point, but it's not official. So you can easily turn up or down the number of worker nodes you have scanning your file systems.
Yeah.
All right. Any questions?
There was a capability to aggregate files into a single tar file and move these single tar files. Do you use anything like that on ingest to minimize the number of files that are going across the network? So this is for people who have a very large number of small files.
Right. Not presently. I'm not sure that's come up before either. You know.
Yeah, usually in these contexts. So from a landing zone point of view, you know, that is the starting point, but there's always an associated data movement. Well, what we saw more here was more of a scanner. And so that's where we treat the file system itself as a single point of truth. And so the data movement there is considerably more granular, I guess, because we're just not assuming that we're going to be bulk moving large bunches of files. From a landing zone point of view, that would make a lot more sense though.
We had a site in Wisconsin that had 1 million files, 1 million very small files.
Yeah.
And trying to move 1 million small files just is not worth it.
Well, it'll beat the catalog up because that's all metadata operations. It's not actually, you know, data movement operations. So sure, absolutely. No, we also have, well, it hasn't been demonstrated here from the ingest point, is the ability to stream files. So if you look at, say, some of these microscopes that have very, very large runs, they keep appending to a particular file in place. And so we now also with automated ingest have the ability to detect the deltas and simply update the catalog with that data movement. So we can periodically stream data from other instruments as well. So it's really designed to, as I said, move that policy as close to the source of the data as we possibly can. Even from a provenance point of view. So, you know, we know exactly where the data came from and how. Well, how's not here, but
How's not here. And to demonstrate the point about configuration, not code, that capability is done simply by overriding one method in that event handler that we had. And you just put append instead of whatever operation we have.
There it is. Anything else? No? All right. Well, thank you.
Very good.